Hello everyone, this is the second tutoring session where we're going to be going over some naming from chapter 3 and naming from chapter 2 and mass relationships from chapter 3. And so you may find it helpful when we're going over the naming to refer to page 61 of the textbook. They have a really nice concept map that helps with the naming. And so the first couple of examples, we're going to be working with ionic compounds. And with ionic compounds, you need to pay special attention to the charges. And so we're going to start with potassium bromide. Potassium is number 19 on the periodic table, and that charge is +1. And bromide, also bromine, is number 35, and that charge is -1. And we learned that we can cross our charges to make them add up to 0, which would just be K1Br1, which is simply just going to be KBr. And so for our next example, we're going to have aluminum oxide. So aluminum is number 13, and that charge is +3. Oxide is oxygen, that charge is -2. We're going to cross our charges. So we're going to have Al2O3. And when we do our math, just to make sure, 2 times +3 plus 3 times -2 is going to be +6 plus -6, which is going to equal 0, which is what we're looking for. So we're going to move on to the transition metals. And with transition metals, we have to pay attention to the Roman numerals because our metals can have more than one charge. And so these charges are denoted by Roman numerals. So I'm going to start with the first one. Manganese 2 oxide. Manganese is number 25 on our periodic table, and there with our transition metals. And here manganese is +2. And oxygen is -2. And if we cross our charges, we're going to get M2O2. But we want to reduce that down, right, because these are both divisible by 2. Sorry, that should be an N, Mn. We want to reduce that down to MnO. And just a little brief preview of what we'll be going over in a little bit. The formula that's reduced down to the lowest ratio is called the empirical formula. So when we write our formula, we want the empirical formula, or the lowest ratio of elements to one another. And so now we're going to have manganese 3 oxide. So this time it's +3. Oxygen is -2. We're going to cross our charges, and we're going to get Mn2O3. And we can't reduce this down anymore, and so if we just check our math real quick, we're going to have 2 times +3 for manganese plus 3 times -2 for oxygen equals 6 plus -6, and that equals 0. So we're good to go. So now we have manganese 4 oxide. Now our charge is positive 4, oxygen is negative 2. We're going to cross our charges. It's going to be MnN2O4. And automatically we see that we can reduce this down. And again, we want to have our empirical formula with the lowest ratio, so we're going to have MnO2. And you can check your math there just to make sure it adds up to 0. I'm just going to write a reminder up here. We want the empirical formula. Okay. So we're going to move to covalent compounds, and with covalent, remember this is where we have our prefixes with mono, di, tri, and so forth. So we're not so much looking at charges as we are the prefixes of how many things are in here. And so one thing to note is that with mono, the chemistry gods, for whatever reason, decided that mono would be noted in the second element. And so we see here we find mono in our second element. But mono is not in front of this bromine, but it's understood to be there. So it will not be noted in the first element. But the other prefixes are noted in the first element. So if you have a covalent compound that doesn't begin with anything and it just begins with the name, we're going to assume that there's one there. So in this case, for bromine trifluoride, we're going to assume that there's one bromine because we know the mono is not going to be noted in the first element. So we're going to say Br1, right? We don't have to write the 1, but I'm just writing it. Just for clarity. And then we're going to have trifluoride. Tri means 3, so we're going to have 3 fluorines. So BrF3. And this next one we have dihydrogen monoxide. So we have 2 hydrogens and 1 oxygen. 2 hydrogens, 1 oxygen to give us water. And so we went over naming because naming is helpful to know when we move into chapter 3. And so in chapter 3 we're introduced to this idea of atomic mass. And we learned this general setup of the periodic table in chapters 1 and 2, where to find what kind of information. And here we find the atomic mass. And the atomic mass is the average mass of the naturally occurring mixture of isotopes found. And so what does that exactly mean? Well, it means that if we have a huge amount of just regular pure hydrogen, a few 2 or 3 of those are going to be just a naturally occurring isotope, and we learned that an isotope just means that you have a different number of neutrons, and so you have those few little hydrogens don't have an atomic mass of 1. It'll be a little bit more because they have more neutrons. And so when we look at the average of all that put together, that's why our atomic mass is 1.01 and not just 1, because we're taking into account those isotopes. And so we get introduced to this idea of a mole. So what is a mole? A mole is just simply a unit used to describe a large number of atoms. And so we can relate this to real life, like when I go to the grocery store and say I'm making a bunch of cakes. I'm not going to say I need 12 eggs. I'm going to say I need 1 dozen eggs, because that's how eggs come, and it's easier to just say a dozen or 2 dozen. And it's similar to shoes. I have, because I'm a typical girl, I have 20 pairs of shoes. I'm not going to tell you I have 40 shoes, because we measure shoes by the pair. So I have 20 pairs, which equals 40 shoes. So what does 1 mole equal? Well, 1 mole is equal to 6.022 times 10 to the 23rd atoms. So instead of saying, well, I have 6.22 times 10 to the 23rd atoms of hydrogen, I'm going to say I have 1 mole of hydrogen. It's just easier to say and easier to deal with. And so we're going to be talking about this relationship between mass, between atomic mass, moles, and atoms. And we're going to talk about how you kind of switch from one to another. So how do we use moles to solve problems? What are we going to be using this for? So if I'm given a certain grams of something and I need to know the atoms, or if I'm giving moles and I need to know grams, this is the relationship we're looking at. And so if I have 1 mole of oxygen on the periodic table, we know that oxygen is 16 grams, depending on which periodic table you have. And the conversion factor, 1 mole of oxygen, is going to have 6.022 times 10 to the 23rd atoms. If we have 2 moles of oxygen, we're going to have to multiply this number by 2 to get the number of atoms. And then, of course, we multiply the atomic mass by 2 to get 32 grams. And so we're going to fill in this table up here for chlorine. We did this for oxygen. Now we're going to apply this idea to chlorine. And so when I had 1 mole of oxygen, I had 6.022 times 10 to the 23rd. Well, that doesn't just apply to oxygen. That applies to any element. 1 mole of any element will be 6.022 times 10 to the 23rd atoms. So 1 mole of chlorine is also going to be 6.022 times 10 to the 23rd atoms. And from the periodic table, we know that's 3.45 grams. And so this should say 2 times. So if we have 2 times the number of atoms that are in 1 mole, that must mean we have 2 moles. So we have 2 moles of chlorine being 2 times the number of atoms found in 1 mole. And so here, just like with oxygen, when we had 2 moles, we need to multiply the atomic mass by 2. So you're going to have 2 times 35.45 grams to get the atomic mass of 2 moles. And so if we have 4 moles, then we're going to have 4 times the number of atoms found in 1 mole. And so then we need to multiply our original atomic mass times 4. And you can figure that out with your calculator. And so we're going from moles to atoms using Avogadro's number. I know this can be small, this can be hard to see up here in the corner. But we can go from, we're going from moles to number of atoms, we're using Avogadro's number. And we go from mass to an element to moles of an element, or vice versa. We have to use the mass number found in the periodic table, which is what we're doing here. You know, we have 1 mole is going to be the mass number, which is 35.45 grams. So you can kind of use this map to kind of help guide you through the relationships between these things. And so we're going to have a word problem. Yay! How many moles of atoms are in 6.46 grams? And so when we're looking at a word problem, it's important to figure out what are they asking. Well, they're asking for moles, so I need to find moles. And then the second thing that's important to ask yourself is, what do we know to help us find that information? Well, we know that 1 mole is equal to 6.022 times 10 to the 23rd atoms, but they didn't ask us for atoms, they asked us for moles. And we also know 1 mole is equal to the atomic mass of the element found in the periodic table. And so we're given 6.46 grams of helium. And so we need to convert to moles. And so we know that 1 mole of helium is equal to its atomic mass, which is 4.003 grams. And here we can see that our units will cancel. Grams are going to cancel with grams, and it's going to give us moles. Moles. And that's going to be about 1.61 moles of helium. Which makes sense, because if we are taking 6.46 and dividing it by 4, we should get a little bit more than 1. So this answer does make sense according to our math. And so we're going to take this one step further, and we're going to say how many atoms are in 6.46 grams of helium. And so when we're using this map up here, we're given, right, we're given weight, and it's asking for number of atoms. And so we just found the moles. We know the moles, 1.61 moles. Or we can start from the beginning with 6.46 grams. And so for starting, what are they asking for? They're asking for atoms. We're given grams, and we know that 1 mole of helium equals 6.022 times 10 to the 23rd atoms, which is what they ask for. And that's equal to the atomic mass, or 4.003 grams. And so if we're given 6.46 grams, we're going to use our information from the problem above, and we're going to we know that 1 mole of helium is equal to 4.003 grams. Okay, well now our grams are canceling out. Well, that's good. But we're stuck with moles, and we're looking for atoms. And so in order for moles to cancel out, we need moles on the bottom, and we know that 1 mole helium is equal to 6.022 times 10 to the 23rd atoms. Now we can see that all of our units are going to cancel and we're going to be left with atoms. Cross out our moles. And we're left with the number of atoms. So this final answer should be 9.70 times 10 to the 23rd atoms. Because we're going to multiply across the top and divide by the bottom. And this is our final answer. And so now we're going to move on to molecular mass. So molecular mass is simply just the mass calculated from the periodic table. And so we look at carbon. What is carbon's molecular mass? So carbon's molecular mass, number 6 on the periodic table, is 12.01 grams. Oxygen, 16.00 grams, depending on which periodic table you have. So carbon dioxide, this is where the naming comes in. We have carbon, and there's only one, because mono is not noted in the first element. For dioxide, we have 2 oxygens. So that's going to be 12.01 for the first one, for carbon, plus 2 times our oxygen, which is 16.00. I'm just going to write O for oxygen, so we know what that is. And so that's going to be 32 plus 12.01, which is going to be 44.01 grams. And that is the atomic mass, or this, excuse me, molecular mass of carbon dioxide. This is our final answer for this problem. So we're simply just adding the weights together from the periodic table. And so we're just going to do a few more examples to wrap up. So sodium chloride. So we have to figure out what the formula is for this. So with sodium, that charge is +1. Chlorine, it's -1. So they're going to equal up to 0, so it's just NaCl. Our molecular mass is going to be 22.99 for sodium, plus chlorine, which is 35.45. And that's going to be about 58.44 grams of NaCl. And so KCl, if we're going to go back to our naming, simply going to be potassium chloride and then when we calculate our molecular mass, we're going to have 39.10 for potassium. We have to make sure our charges cancel out, which they do. It's +1 -1. Sorry about that. Plus chlorine, which is 35.45. This is going to be about 74.55 grams of KCl. Now we have aluminum chloride. Aluminum, which which our charge is +3. Cl, which is -1. So now we're going to have to cross our charges. So we're going to AlCl3. And so when we find our atomic mass, it's going to be aluminum, which is 26.98 grams for aluminum, plus 3 times, right? Because we have 3 chlorines, 3 times 35.45 for chlorine. And that's going to be about 133.33 grams of AlCl3. And that wraps it up for this video. And so what we went over was naming compounds. We went over chapter 2, ionic, transition metal, and covalent, the relationships between mass, moles, and Avogadro's number, and molecular mass.